Okay, number 6, we're asked to determine the solution to each system of equations we looked at in 6. So we'll start with the easy one, the first one. The reason that was so easy was we recognize that if you double this, you get this equation, which means there's a infinite solutions because these two planes are actually the same plane. They're lying on top of each other. So every single point is a solution. Yeah, that's a nice one. If we try C, however, we figured out the intersecting line, so we're going to have to figure out the parameters that make up that line. Now, there's a bunch of ways you could approach this one. You could eliminate the x's, the y's, or the z's. You do have choices on here. I'm going to start with the x's just because it comes first. There's nothing wrong with eliminating the y's if you'd wanted to do that, but it may be a slightly different than what's in the back of the book in terms of your direction might be a scalar multiple now instead of the same direction that we get. X minus x is gone. I get negative 2y, I get no z's, and I get 4. Well, that's kind of nice because I can solve for y right off the bat. If I go back and plug it into one of my equations, for instance, x minus y plus 2z equals 2, I got x minus negative 2 plus 2z is 2. I end up with x plus 2 plus 2z equals 2, or in other words, x plus 2z equals 0. Okay, well, I can't really go any further with that, right? I got two variables, but only one equation. So here's where that parameter comes into play. That's that ZBT. Now I can keep going. I get x plus 2t equals 0. Or in other words, x equals negative 2t. So now I have a solution for this line. It's a parametric form. So you could write it as vector form if you wanted to. You could say that r equals x value of 0, a y value of negative 2, a z of 0, plus t in the direction of negative 2, 0, 1. It doesn't ask you for vector form, but you could put the vector form if you wanted to. Parametric is just fine. Okay. If we try that or E, again, it doesn't really make a difference which one you eliminate. It's kind of your choice. I'm going to take the second equation and times it by 2 so that my equations eliminate the x's again. So I'm just going to rewrite number 1, okay? Same equation I had there. And then underneath it, I'm going to write the second equation, but multiplied by 2. Again, if you chose to eliminate something else, it'll still work. Just have a scalar multiple for your direction vector. Okay, I'm adding this time because my x's are opposite signs. So 3y, 4z, 4. Can't really go a whole lot further here, right? So let's pick a parameter. Now, it doesn't matter which one you make your parameter, totally your choice. I think in the back of the book for this one they let ybt, but you could let zbt. It doesn't really make a difference. If y is t, then I get 3t plus 4z equals 4, or 4z equals 4 minus 3t. If I divide everything by 4, I end up with 1 minus 3/4 t. There's a parameter for z. Let's go back up and get x now. How am I going to get x? Well, I have an equation, negative x plus 2y, but y we said was t, using this equation, okay? Plus z, oops, plus 2t, plus z, what did we say z was? Z was 1 minus 3/4 t equals 1. Now I want to solve this for x. So I'm going to put the x on the other side. Bring the 1 over and make the x over here. Okay, so 2t minus 3/4 t. Well, that's 5/4 t. And 1 minus 1, well, those are gone. So there's our equation for x. And again, if you wanted to, you could put into vector form. You'd have a point of 0 for x, 0 for y, 1 for z, plus t, 5/4 for x, 1 for y, and negative 3/4 for z. Now, a way of you might be able to check is your answer that you wrote down a scalar multiple of this direction vector? If it is, then odds are you did the right way. Okay, and that's how we do that question there.